So part of my setup works, but the other does not. So I'll have to depend this on. So I'll show you some of these slides, and I'll see what I'll tell you a little bit, and we might have to use the board for actually writing stuff. Okay, so we'll move to that. All right. So quick start with the announcements. So last time I didn't get to show you the course web page, the Canvas page, and so on. So this done last time. So let me just show you the course home page. So this is how it should look, okay? And so you have a rough set of topics, and there's a bunch of so the logistics we have discussed last time, and so the office hours I said is 1 to 2 p.m. after class, okay? And the exams I also discussed last time, and so the textbooks I listed a bunch of textbooks. There's no single course that will cover all the single book that covers everything that you're going to see. Okay, so but these are all excellent textbooks, and I encourage you to have one of them, and for the rest you just use the notes that we provide. Okay, so that's the thing. And so last year I had this textbook, this as an official textbook, where it turns out that most people had difficulty following it. So this year I thought it's just best to not have an official course textbook. Okay, so you can use any of these references. All right, and so there's also a course schedule here that I wanted to talk about. And so there's a homework 0 that I have posted. Okay, so this, so I have an official due date of this Monday. Okay, and there is on Canvas, you will also see this as some place where you can actually submit this. So I hope all of you have checked out the Canvas page. Okay, so if not, do so, and you'll see a place where you can submit your assignments. Okay, and so this is a good exercise for you to just see how grading is done. And if you're not that familiar with LaTeX, Markdown, and so on, so this is a good time to test your skills. Okay. So these are 5 simple problems that should not take you more than half an hour or so per problem. Okay. So, and it will give you some sense of how to write proofs. Okay. So, any questions about the course setup? Okay. So. All right, and the TAs have come up with office hours, so it's official. I think that we will have 4 TAs. Okay, and so that's Hong, who is here, and I also saw Shravan somewhere. Yeah, okay. So 3 of them are here, and Amin, who is I don't know if he's here. Okay, so. Yeah, and these are their office hours. I don't know if you want to note them down, but these will also show up on the course webpage soon. Okay. So this is that. And instructor office hours are 1 to 2 p.m. after class. Okay. Yeah.
Is there a location for the TA's office? Where's
yes.
the location?
I forget the room name. So there's one room in the CS department where all the course, where all the TA office hours happen. Okay, so what is it? Do you remember the number of that room?
They have changed the old room.
Oh, they've changed it now.
Yeah.
Okay, but this is something that you should know. Okay, so that we should add a link to that also. Find out the name of the room and let me. Yeah, that's a good point. Okay. All right, and I just wanted to know that today I need to quit in the afternoon, so I won't be here. So today is office hours are cancelled. Yeah.
Are you planning on releasing the solutions to the homework after they're due?
Yes, I will release them about 10 days after they're due, because the late policy allows you to submit until 10 days after. Yeah. All right. So any other things about logistics? Alright, so the other announcement that I wanted to make is that homework 1 will be out tomorrow. And this will be more on the background side of things and a little bit about data structures. Okay, so that's what homework 1 will be about, because we haven't really done much. So that's what homework 1 is.
Is homework 0, is that worth points or is that necessary?
Yeah, homework 0 is optional. You don't even need to submit it. But I would recommend that you submit it just to get some feedback on how people grade things and so on. Yeah. All right. So I wanted to start with a quick recap of the last lecture, right? So we said we had this very basic question. We said that, okay, so suppose you have a sorted array, which I call A, and you want to find if there is an element X in it. We said there's the standard algorithm called binary search, which at every point maintains like a subarray, and each time you look at the midpoint of that subarray, and if it's smaller than X, then you recurse on the right, and if it's larger than X, you recurse on the left. Okay, if it's equal to X, then it's great, you've already found X. Okay, so that was the binary search algorithm, and we proved correctness. Okay, so this was just an exercise in actually showing how you show the correctness of algorithm. Okay, so that was and we also analyzed the running time of this algorithm. Okay, and we saw, and as I was saying, so there's a very simple general way to analyze running times. Just go through the algorithm and figure out what each step takes. Sometimes you will have some recursive calls. Try to parameterize the recursive calls in terms of some kind of a recursive form. So usually there will be some parameter. In the binary search example, the parameter that we saw was, do you guys remember what the parameter was? Right, so there was every recursive call had a starting point and a starting index and the ending index. So the difference between the two, which is essentially the length of the subarray, was the measure of the problem size. And that was what it showed. Okay. And yeah, so one thing that came up is sometimes correctness proofs can be tricky even though the algorithm is simple and kind of intuitively obvious, right? So you may have to figure out the right inductive statement. And yeah, we also said that having the right proof also lets you realize where you're using the different hypotheses in the problem. Okay. Like in that case, the fact that the array was sorted was being used in one particular step, right? So we realized where that was. So, right. So sometimes proving something is correct can be a bit more subtle than you think, and it often requires a bit of thought. Alright, so today's plan is a little bit about the basics of data structures, and we'll also see some more examples of analysis of running times. So that's what we'll do this time. Okay, so what are data structures, right? So the main so the point of data structures is, how do we store data, right? So you have your input to the problem, you have some data that you generate potentially while running the algorithm, and then how do you store all of them? And that's basically the study of data structures. And the first thing you should ask is, does it matter how we store these things? Like, I mean, the input is some input. Why do you need to process it and store it in some other way? So that's one question that you've got to think about. And the other thing is, what are the relevant relevant parameters of a data structure? So that's the other thing you've got to keep in mind when you're thinking about data structures. So let's see. So we'll see examples where, in some sense it matters a lot how we store the data that we are doing. Okay, because you've got to be able to make the right queries in an efficient way. So often for the running time, it matters how exactly we store the input that we are giving. All right, so let's see a very simple example. So this is what I call the Scramble problem, right? So you have a dictionary of words. It is, let's say it's a long dictionary, and so you want to store a dictionary in such a way that, suppose you are given a word query, okay, like you're given a new word W and you're asked, does this word exist in the dictionary? Okay. You want these kind of queries to be done very quickly. And suppose you have some capital N words in the dictionary where N is really large. Now, how would you solve this problem? Right? So there are two aspects to this. Right? So one is I'm only asking you for the query to be small. I mean, you could have done a lot of pre-processing to the dictionary. So you can store the dictionary in whatever form you want. But I just want fast query. Okay, so suppose you did not do any processing, right? Like I was asking this question, does it matter how we store the input, right? So suppose you just had a dictionary as it is, then how would you solve this problem? What would be like a very, very trivial solution to this? Sorry?
Linear.
And what do you mean by linear?
Go through each element in the dictionary and find out the
Yeah, so the most naive solution is you have a dictionary, you have a query word. So you just say, okay, I just run through the dictionary and check if this word equals whatever word we are at. Right? And this takes time n, at least n, because there are n words in the dictionary. And there's also some time for comparison and so on, which let's say we ignore for now. Okay. So this is one way of doing things. Okay. And yeah, so can you think of another obvious way but a better way? Yeah.
If we know the starting letter of the word that we want to search, we can go to that. I would say that we would construct a tree and we just check left or right. If it's a dictionary, so it's arranged alphabetically.
Okay.
So if we check the first letter, then we'll go to the tree of that letter. Then
so you want to store the dictionary as a tree, right?
Yeah.
That's the main idea. Okay, so that's so we will come to that in a little bit, right? So, but given that you've seen binary search, this is exactly the same problem, right? Because you have a bunch of things, you want to know if a given word is in that list or not, right? So suppose you had a sorted list of words, then you could do binary search. Because you can always define some kind of a comparison operator between two words. Right? So let's say a lexicographic order. Okay. So that would give a dependence which is log n. So it's much better than what we have seen now. So is this improvement clear to everybody? Okay, so this is another obvious solution. So, yeah, so given I can't write on these slides, I will probably switch off this project. Can everybody see that projector and the text written in that? Let's say the smallest font is that. It doesn't matter. I don't have anything even in that font later on. Okay, so we've got a trivial solution, which is O of n time. This is just brute force lookup. Okay, and you also have a trivialish solution, which is O of log n, and that is binary search. And now you could ask, okay, so is there so both of these depend on n, which is the number of words in the dictionary. Right, so you could ask, is there something that's independent of the size of the dictionary? Okay. Yeah.
Hash. Yeah, I was going to say you could use a hash set or a hash map.
So hashes are, they hide complexity in ways that you don't know. Okay, so the expected hash time is often constant, but yeah, but it often, if you think about it hard enough, you realize it's closer to log n. Okay, so yeah, so let's yeah, so that is a valid solution. But the one I want to discuss is something that he was just suggesting. Okay, that I mean, maybe you want to store the words in the dictionary in the form of a tree. Okay, so how would you do this? So this is so these are what are called prefix trees. Okay, so the idea is store the dictionary as a tree. Okay, so this is the rough idea. And how would you implement this? Right, so that's the thing that you want to understand. Okay, so somehow we are saying first process the dictionary, okay, and store it as some kind of a tree. Right? And what would be a natural way to do this? So let's say you've got some words, right? So you have apple, right? So you've got some bunch of words like this. And how would you store them as a tree?
Okay, so you could have a root node with 26 different nodes off, branches off of it, where each branch is equivalent to one letter. From
Okay.
the root node, each of those branches refers to the first letter of the word. So say the word is apple, we would go down to the A and then do the same thing as the tree above for the second letter and so on. And then to check if something is in the dictionary, we just navigate down all the branches for each letter until we either complete the path or there is a path down.
So what do you do when you're actually building the dictionary? How would you know that, for example, apple is a word and let's say apples is also a word? So you've got to be a bit more specific, right? So how would you mark whether something is a word or not? Yeah.
Well, you could iterate through each character, right, and split them all out separately, and then organize it down that way.
Right, so that's what he was suggesting, right? So every letter is, you go letter by letter and then you have this.
You can have an extra letter, say N, and whenever you see a word like apple, after E you can go to the end letter also. Like instead of 26, you
Okay.
can have 127.
Yeah, so that's one way of doing things. Okay, and an easier solution could be at every node of this tree, you also have a Boolean variable that says, oh, is this actually a word or not? Okay, so you have the tree like this. Okay, and at every node, have a Boolean variable indicating if the word so far. So every node corresponds to something, to some put candidate word, right? Like this is a candidate word AB. Okay, like this node corresponds to the candidate word AB. And you can have a Boolean variable which indicates if the word corresponding to you. So let's give a name here. So let's let's call this node some alpha. Things word corresponding to alpha is in dictionary. Okay, so this is how you would. So this is the data structure, right? So it's basically a tree, and for every node you have this extra Boolean variable that it's a true or a false. And now when you are actually going through the dictionary, when you are building the data structure, you would go through every word, okay? And you would go through this tree and mark this Boolean variable as true for the appropriate. Okay, and if you think about it, building the tree, building the data structure takes time, which is linear, right? So it takes time. But it's just that now, once you've built this data structure, the query time is very fast. And this is the difference between the previous trivial solutions and this. Right? Like, so once you've built this data structure, the query time is fast. Okay, and this is often what happens in data structure. Okay, so when you're constructing the structure, could take more time. But once you have it, you can do queries quickly. Alright, so that's, and these kind of things are called prefix trees or trials. Okay, so these are called prefix. Okay, so is this data structure clear? So this is just an example of a very basic data structure, and it can store any set of strings. Okay, so a dictionary or something. So that's what this is. And now you can ask, so what kind of operations can you do on this data structure? Right? And you can do things like adding or removing a word. How would you add a new word? Yeah, you just do what we did, right? You just go down, and if there is no node, you create the nodes, and at the end you mark this Boolean variable as yes, as true. That's how you would add a word. How do you remove a word?
Change the Boolean false.
Yeah, so you can change the Boolean to false. That would definitely delete it. Every once in a while you may want to do some cleanup, right? Because now you might have portions of the tree that are just simply never used. Okay, so you might want to do that. But you don't have to. That's only for the purposes of efficiency. So, alright, so that's that. And looking up a word is also very simple, right? You just go to the tree, see if the Boolean variable is true or not. Okay, and yeah, counting prefixes. So this is, what I mean by this is, suppose I give you a prefix which, let's say CO, and ask you how many words start with CO. Okay, how do you do operations like this? Correct? Yeah, maybe somebody else.
Can you just go into the tree and just see C and O, and then just see how many child off of the O index, and just do a count.
Right. So what you want to do is you will have a subtree, and you want to count how many words are actually in this subtree, right? And you'll need a clean way of doing this. Okay. So it turns out you can do this. You will see this in your homework. So it's very simple, but you can do this. Okay. So this is so you can do this also pretty efficiently. So while building the data structure, you can kind of maintain additional information, and that allows you to do this very quickly. Okay. So it turns out these kind of operations can all be done in time that's proportional to W, which is the length of the word being looked up. Okay. So what you said is not quite a solution, right? Because do you see why? Because you have to go through each of the branches, and you have to do essentially a whole search in the tree to figure out how many nodes are there. That could actually take a long time. So what's, yeah, so you have to do something a bit more clever to be able to do queries like this. Okay. So, alright, so that's that. Right? So turns out you can do all of these kind of operations in time which is proportional to the size of W, okay, which is the length of the word. Alright. Any questions on that? Okay, and so that was just one example of a simple data structure which stores strings. So in general, when we think about data structures, what we've got to think about are these questions. Okay, the first thing is, first you need to know what kind of data this data structure stores. Okay, like is it storing strings, is it storing numbers, or it could be more complicated objects as well. And then you've got to think about, okay, what are the operations that are allowed. Common things are like you can add stuff, delete objects, and count, and so on. And you want to understand how long it takes for each of these operations. Okay, so that's the time of these. That's the time it takes for each of these operations. Okay, and in some cases, you also want to know what the space usage of this data structure is. So in this case, it turns out that the space usage is not much, but sometimes you might want to store additional information, and in those cases, you may want to think about how much space you're using. So that's so these are the rough questions that should be in your mind when we are thinking about data structures. Okay? And very often, you may have no idea what exactly the data structure is doing or how it implements these kind of operations. But all you've got to know are these parameters, right? So it's like, okay, what kind of data does it store, and what operations can you do, and what is the time for each operation? Okay. So, and this is what you will find in most APIs for data structures, right? Like there's this STL for C, and there's a lot of libraries for various programming languages, and these are essentially what you care about, right? So you don't. As a user, you may not care about how these things are implemented, okay, but you should know what is being stored, what are the operations, and what's the time being used. Okay, so that's how we will think about data structures for now. But for a few data structures, you should know how they work. Okay, so one simple example is that is prefix trees. Okay, the other example we will see are binary search trees, because this is another data structure that's used all over the place. It's used almost everywhere, and hopefully all of you have seen this in some form. Okay, so what are binary search trees? So let's go through these questions that I wrote down and answer them based on what you guys should know. Okay, so what data do binary search trees store? Yeah.
I would say anything that can be compared to another element.
Okay, so any any set of objects for which there's a total ordering, right? So there's an ordering of these objects. But in particular, let's just think about them as integers. So binary search trees. The simplest example is integers. So the kind. That's integer. Okay, and what kind of operations can you allow? I guess there's a lot, but let's say I want to allow add, I want to allow delete, I want to allow query. By query, I just mean does X belong to the data structure. And yeah, so let's say I have these things for now. Okay. So what is the time taken for each of these things? In whatever implementation you guys have seen. Okay, and yeah. So what data structure are you thinking of when you think of this? I mean, to achieve log n, what would be kind of the kind of tree that you should build? Yeah, so you've got to build a balanced tree, and so there are many things that you must have seen. There are what are called ABL trees, red-black trees, and so on. Which allow you to do all of these operations in something like log n time. Okay, where n is the number of elements in the tree at this point. Okay, so I mean, many of these data structures have this nice property that if you add a whole bunch of elements and you delete all of them, then the operations get faster. Okay, so that's interesting to know. Okay, so, all right. So this is add, this is delete. All of them are log. Okay. So hopefully all of you have seen some implementation of binary search tree, balanced binary search. So that's that. And what is the space usage of these things? Yeah, so these are just linear. So it's okay, so you just have essentially one or two nodes, one node per entry and maybe a few extra ones. Okay, so space usage is overfed, and these are kind of used in a whole bunch of places. Okay, so this is one of the very basic data structures that we use. Okay, and for most applications, you don't need things that are much more fancy than these. All right, so but you've got to remember a few subtleties. Okay, so one thing is that perhaps some updates are slower than others. Okay, so it could be that some updates take much longer, or maybe some of the operations could occasionally take a long time, but they are pretty low on average. Okay, but they are pretty quick on average. So this is something that you've got to keep in mind, and we'll see some examples of this. Okay, so these are okay, how many of you have heard the word amortized analysis? So what does it mean?
So when you do like a lot of them, and then you look at the average time, how all of them takes.
Yeah, so amortized analysis is basically you do, let's say, n operations of a certain kind, and you essentially divide the total amount of time by n, and that's like the amortized time. Okay, so it's just an average. Right, so this is something that people often look at. Right, so it's so yeah, any commonly used data structures you know where this actually matters. Well, like sometimes the updates could be very slow, but on average they are quick. I mean, I'm sure all of you know this data structure, but you probably don't know that this is what it does. Okay, so the standard example for this turns out to be this C++ vector, if you guys use it, or any variable sized array. So how these variable sized arrays work is that they always they want to use a space utilization that is that's proportional to how many things you actually have in the array, right? So occasionally when you increase, so initially they will have an initial size of, I don't know, 20 or something, and as you keep adding elements, if you add more than, let's say, 15 elements, they will reinitialize space and have an array of size 40. Okay, and now that step could take a long time. Okay, but on average you'll be really fast. So that's what's called that's one very common example of amortized analysis. Okay, so like variable length array. Okay, if you think about it, an array must actually allocate all the space, right? So if the size is varying, then you have to occasionally reallocate space, and that could take a long time. Okay, so in the worst case, adding an element could take a while, but on average, it will be pretty fast. Okay. So this is one common example. Okay. And another common thing that happens in data structures is probabilistic analysis. And here what we mean is that occasionally an operation could take a long time, but with good probability they take a small amount of time. So it is possible. So with high probability, operations are fast. Okay, so I don't know if you guys have seen examples of this. Have you seen examples where you have like probabilistic ways of doing things? I guess you must have seen it. Right? So most of hashing is essentially like this. Okay, so you can have a hash table, and every element. So you will have a table that looks like this, and you will have, let's say, strings going to hashes, right? So you have strings of a certain length that go to these things, and these will be assigned at random using some random hashing function. So with good probability, with high probability, you can say that each bucket receives very few elements. Okay, and so that will be the worst case lookup time. Okay, so the lookup time would be small on average or small with high probability. So this is something that you can show. When we study randomized algorithms, we'll see examples like this. Okay, so this is why I was very reluctant when somebody suggested hashing for string. Okay, because it's good on average, but occasionally it could take a long time. All right. So these are some subtleties that you've got to think about that show up when we study data structure. But the basic questions are very simple, so you just have to understand these kind of things. Alright, so the third example, which is another simple example, is storing graphs. Right? So you've got a graph which is a bunch of vertices, bunch of edges. Let's think of undirected graphs for now. So how would you store a graph?
Matrix, adjacency matrix.
Okay, so that's one of the natural things, right? So, and what are the dimensions of this? So let's say you have a graph G which is V comma E. V is the set of vertices, E is the set of edges. So what is what would an adjacency matrix look like? So so it's a V by V array, which is 0 ones. Okay, so 1 if there is an edge, and 0 if there is an edge. So this is one way to store a graph, right? So, and yeah, right. So you could ask things like, how long does it take to find out if U and V have an edge? So this is just constant lookup, right? You just see if this ij or uv, right? So you see this entry corresponding to uv and you see if it's a 1 or not. So this is a very quick operation in this way of writing things. Okay. But what if you have to add a vertex? Yeah.
What if we store a graph in the form of array of linked lists?
Yeah, so you want, so now this becomes complicated if you have this sort of, I mean, if you just have a fixed array, it becomes problematic, right? So you have, I mean, you've got to change the array to something that has a v plus 1 by v plus 1, and you've got to think about how you do this. And this could be messy. So, and one way of overcoming this is think of a variable-sized array of arrays, which essentially stores. So that's one possibility. But this is in general a messy operation if you have something. Another thing you may want to do is return all the neighbors of a vertex. So how long does this take? Okay, so this takes O of V. And this is again kind of suboptimal, right? Because suppose a vertex just has 10 neighbors and the graph is a huge graph with like a billion nodes. Okay, so like let's say you have like a Facebook graph or something and a person has 100 friends, right? So you don't want to go through the whole, all the people in the world and see if this person is a friend of this guy or not, right? So that clearly sounds suboptimal. So this way of storing things is good for finding out if you and we are friends, but otherwise it's not so great. Okay. So what is the other obvious representation? Sorry?
Sparse matrix.
Yeah, and how do you store a sparse matrix?
We only store the locations where the connection is, edge is there, otherwise we don't store it.
Okay, and in words of graphs, so this sort of a thing is called an adjacency matrix. Okay, so it's yeah, so sparse matrices are essentially adjacency matrices, adjacency lists with weights. Okay, so let me mention that. So this is another standard way to store graphs. So this is called adjacency list. So as the name suggests, you have a bunch of lists, right? So for every vertex, you have a list. So you have list of we have a list. We call neighbors of V. Okay, so this is a list that has a set of all neighbors of this vertex. Okay, so for instance, we could have lists like 1, 2, 4, and 1, something like that. Okay. So the size of this list is basically the number of neighbors that V has. Okay. And now you can ask yourself, what is the time for each operation, right? Like suppose I have. Actually, let's come to the first question in the end. But suppose I want a list of all neighbors. Okay, so this is trivial in this setting, right? Because I can just go through the list, output all of them. Adding a vertex is also trivial because I just have to create a new empty list. Finding out if U and V are find if U comma V are connected. How long does this take?
Number of neighbors we have.
Yeah, so this is this takes time, which is kind of, if you want to be a bit more careful, you can say it's like min of number of neighbors of u, comma number of neighbors of v. So you will look at whichever is smaller and you will actually go through that list and see if the other guy exists. Okay. So this is one thing. Can you think of speeding this up? Yeah?
Instead of a list, you could have a set and then just do the intersection of the set.
Yeah, so instead of a list, you can actually store a binary tree or something, right? So you can store a binary search tree instead of a list. A set is essentially a binary search tree, right? So you can say you have, instead of a list, you store a binary search tree, balanced binary. Okay, and this is great because now instead of taking this amount of time, you will have log of this. Yeah.
The field when you are switching, then when you add the neighbor, it's an age, and then you start update. Now the things that is like 3 all the time.
Say that again, I couldn't.
So let's say right now you are using binary switch, right?
Yeah.
And you could say add the new age.
Yeah.
You do that. And then updating this, you don't need to update the binary switch, right? And this will take like transfer.
Yes. So this is a great point. So what he's saying is that if you had a list, okay, and you add a new edge, which means that for a vertex u, you want to add a new neighbor v prime. Okay. Then if you just had a list, then all you have to do is add v prime to the list corresponding to u. Okay, and that would just be an O of one-time operation because you just add it at the end of the list. Okay. But now if you had a binary search tree, you have to add it to this balanced search tree, which again takes time, which is log of the neighbor. Okay. So this could, I mean, and if the set of neighbors is huge, this could actually be like log n. Okay, where n is the size of the graph. So, but usually logs we treat as small numbers. Okay, so it's so this is a little bit slower, but not terribly slow. So this is yeah. So usually this works pretty well. So right, but this is a great point, right? So now adding new edges is not as simple an operation. So these are standard ways of storing storing graphs. And so what you should know from this what you should realize from this discussion is that there's no single data structure that's probably the best for all purposes. Okay? Like even this pretty bad data structure, which has some bad dependence for these things, is great for some purposes. Okay? And some more fancy data structures like this might be better for some other purposes. Okay? But they are worse for, let's say, checking if U and V are connected. So often what you use depends on what you want to do with this data structure. So this is what you've got to keep in mind. Okay, and very often when you are designing an algorithm, you may want to think about this. Okay, so you may want to say, okay, what kind of queries is this algorithm making? Maybe I want to store the data in a different way. So that is something that you've got to think about. Right? So that's what I want to think about. So yeah, but as I was saying, so this is just one page, one slide summary of data structures. Okay, so you've got to think about what is being stored, what are the operations, how long does it take to do so. All right. So the next thing that I want to do is I want to just pick up from where we left off last time and kind of illustrate maybe a couple of these data structures things also by using this example. Okay, so I remember last time there were a few questions from you guys about how much detail should proofs be and so on. So the more examples I do, I figured that you would get a better sense. So I thought I'd start with a very simple question. Okay, hopefully all of you have seen this in some form before and know a solution to this. Okay, so this is, you're given an undirected graph G and you're given two vertices and you want to find out if there's a path from U to B. So, so how would you solve this problem?
Yeah. Do the first search for app given that we have no other information.
Okay, yeah, so you do some kind of a standard graph search procedure, right? So it's slash depth first search. Okay, and what do we mean by this? So this is, so you are given a graph. I said it's undirected, so it, you are given a U and a V. And hopefully, so how many of you have not seen breadth or depth first search? So hopefully all of you have seen this, and so I'm just going to quickly go through it. The way they work is basically you start at some node and then you start exploring the neighbors, and then you recurse on the neighbors. And you don't want to come back, loop over these things, so you maintain a Boolean variable which says if you've already explored that vertex or not. Okay, so I'm going to write down, so I have a slide with these things. Okay, so you have, so this is depth first search. So where you have, so you have an array which is called reachable, and you set all of them to be equal to false. Okay, so initially you say that nobody is reachable. And now, and then you have a recursive procedure, which at every step, so you try to explore certain vertex W. So, and what this procedure does is, it firstly marks this vertex as reachable. Okay. And then it recursively calls this explore procedure on all the neighbors of W. Okay. And of course, you don't want to you do the same W multiple times. Okay, because then it would just be an infinite procedure that would never end. Okay, so you check if it was not reachable at this point, and only then you explore. Okay, so this is a very so this is a simple procedure. Maybe I'll give you a minute to parse it. And then you basically run explore of U and you return if V was marked reachable by V. Okay, and this is supposed to indicate if U has if there's a path from U. Right? So I want to know how you would argue about the correctness of this very simple procedure. what would you try to prove? What do you have to prove to show that this procedure turns the right answer? Okay.
We can try an induction. So we can say like this is graph G, which is a bigger graph, and then there are sub-graphs in it, like a smaller graph. So we say like for less number of vertices, this is true, and then we can use the induction argument, like we explore all the sub-graphs kind of thing.
So you could try that, but you will run into issues, right? Because what is the subgraph that you want to use it on? So suppose you have U here, and so you have this graph G. What he's suggesting is you want to use induction. What is the most trivial inductive statement you can come up with? You say that this procedure returns the right answer on all graphs of size n-1 with n-1 vertices. And I want to show this for graphs with n vertices. Okay, so this is an obvious inductive statement you may want to come up with. Okay. And what he's saying is, okay, so let's try to use that, right? So assume our algorithm is correct on graphs of size with n-1 vertices. So the reason I erased that of size is that when it comes to graphs, often the size refers to the number of vertices plus the number of edges. Okay, and that's a messy quantity to deal with. Okay, so that's why I just want to say with n-1. Now, how would you use this inductive statement to show? Because the algorithm, as I see it, is not really reducing to a smaller thing, right? Smaller subgraph. Right? So while this is a worthy inductive statement, it's not clear how you would do induction like this. Yeah.
Since we have the check to not revisit a node that we've already visited, effectively consider that node removed from the graph.
Okay, so yeah, so one thing you could say is so this is again what he's saying is an idea that tries to make this line of proof work. Okay, so what he's saying is assume right. So if a vertex has been marked reachable, then you pretend that it doesn't exist. Okay. So how would you complete this proof? And now you pretend that the graph is only of size n-1. Right? But how would you complete this proof? Yeah, so if you think about it, you can in some sense, but it will be messy. So yeah.
So I'm thinking of a different approach. So if there's a path from U to V exists, then some neighbor of U is going to be on the path. So obviously you're going to visit that neighbor. Let's say that I don't know that neighbor's K. So you're going to visit that neighbor, and then either K is if K could maybe also be V. So in that case you're obviously done. But if it's not, then some other neighbor of K is on the path. And I know it's going to be bad if it's going to go along that way.
Okay, so this is a new approach, right? So he's saying, okay, forget about this inductive statement. I will come up with a new statement that says, okay, so if U and V are indeed connected, then there's going to be a path that goes from U to V. And you want to say that U is that V eventually gets marked as reachable. Right? So what he's saying is maybe an inductive statement that says so So let's say this path is V1, V2 up to some VR followed by V. Okay, R could be 0, so let's also consider that possibility. But yeah, so you've got these many vertices in the middle, and then you've got the inductive statement that you may want to say, or rather the statement that you, the final statement that you want is all vertices on the path are marked reachable. Sorry?
Sorry, I was just.
Yeah, I don't know actually where you're sitting is a great place to see this. I hope you can see this. But yeah, so okay, try make it this better. That's okay. Yeah. All right. So you want to so one thing you want to claim is maybe that all vertices on this path are marked reachable, and this would do what you want because V is obviously on the path. So you might maybe want to show this. And now there is a clear inductive statement, right? Like you want to say that vertices up to a certain point, up to here, up to this VI are all marked reachable. Okay? So, and now this is an inductive statement like V1 through, and let me just call this VR. And V1 up to VI are marked reachable. For all others. And this is an easy inductive statement to, I mean, this is a natural inductive statement if you want to prove this claim. Right? So the claim wants to say that all these guys are marked reachable. You say that, okay, I'll show inductively that things up to this point are marked as reachable. Okay? And if you can show this, then you would have shown that all of them are reachable. Okay? So, all right. So is this clear? Firstly, it is clear that this is what we want to show. Like we ultimately want to show that this V is marked reachable, and you may want to show something stronger that everybody on this path is marked reachable, because I mean intuitively that's what's happening in this algorithm. Right? So very often this is what you've got to do. You have to come up with the right statement that you would like to show. Okay? And often that happens by looking at what the algorithm is doing. Then you realize, oh, okay, this is what's happening, and this is how I'm going to prove it. Right? So in this case, it's going through the neighbors one by one, and it's marking all of these things as visited. So in some sense, all the vertices on this path you would expect are marked reachable. Yeah.
Yeah. So what is the difference between this claim and saying that? I mean, what I'm thinking is the claim should be like if V is connected to U, then it will eventually be marked.
Yes.
So is that kind of different from the claim that we are taking?
I mean, ultimately no, but this is, I mean that could be a claim, right? But how would you prove that is the question. Okay? And one way to actually prove that is to have this other claim which you will end up proving, and that would imply what you said. Right? Yeah.
Do something prove by contradiction.
Yeah, you can also prove this by contradiction. Okay, like you could start off with some claim like he was saying and say, okay, imagine there is something that is reachable but is not marked, and then you can look at yeah, because it was reachable, there was some edge from a marked vertex to an unmarked vertex, something like that. Okay, so you can think of proofs like this also. Okay, so those are all good suggestions. So yeah, but for now let's go with this statement, okay? Because it's a very simple statement, right? So you just want to say everybody on this path is marked, and for this there is a natural inductive statement. I mean statement that says if things up to this point are marked, then this vertex is also marked. Right? So that's how I want to show this. Right? So assume this statement. Assuming V1 through Vi are marked reachable. Vi plus 1 also gets marked. So this is a simple thing. If you assume that V1 through Vi are all marked, then Vi plus 1 also gets marked. And why is this true?
Vi plus 1 will be a neighbor of Vi.
Okay, so what he's saying is, let's look at how this algorithm is proceeding. Right? So I said that Vi was marked. Okay, so let's say this is Vi and this is Vi plus 1. Okay. Then this guy was marked as reachable. And when do you mark a vertex as reachable? Yeah, so you mark a vertex as reachable only when the procedure explore has been called on that vertex. That's the only time you're marking things as reachable. Okay. So you know that procedure explore on Vi has been called. And how does that procedure work? First it marks it as reachable, and then it goes through all of its neighbors, and whatever is not marked reachable so far, you will run explore on that vertex. Now Vi plus 1 may not be like the first vertex you will encounter in that list, but it will definitely be encountered in that list, right? Because Vi plus 1 was a neighbor of Vi. Okay? So you know that explore of Vi plus 1 will eventually be called. And once explore is called, you know you will mark it. Okay, because the first step of explore. Okay, so this is a very simple observation. Okay, so what it says is that if V1 through Vi are marked, then Vi plus 1 also gets marked. Okay, and that's it, right? So this shows that all these vertices on the path will get marked. And that in particular means that this final guy will get marked. So are we done here? Does this complete the proof? I mean, does this prove the correctness of the algorithm? Why not?
Show that when there isn't a path.
Exactly, right? So you've got to also show that if there is no path, you will not mark this vertex as reachable, right? Because otherwise you could just have marked everybody as reachable. And yeah, and this is also very simple in this case. But how would you show this in this case? At least what is an intuitive reason why they should be true?
Final vertex won't be a neighbor of the previous one. So explore won't be called for it.
Yeah. So the fact that explore was called on a vertex means that explore was called on some neighbor before and something before that and so on, and you can retrace a path back to you, right? So that's the intuitive reason for this. So you can actually, yeah, so this is actually a formal enough argument, right? Because explore was only, so you can, if you really want, you can have a formal statement that says any vertex on which explore was called actually has a path going from you to that vertex. And this you can prove inductively. So that, and that's the argument, right? So you will only have, so you'll have to show both sides if you want to show correctness. So that's the point I'd like to make. Alright, so this is, again, yeah, so this is a simple algorithm, but But yeah, proving it formally takes a little bit of thought into into what claim you prove. Okay, so the obvious claim like graphs of size n-1 are a bit harder to make them work. So, all right. Okay, so the summary of this proof is that you consider any path from U to V. You want to claim that every vertex on that path is marked reachable, and this you prove by induction. Alright, I forgot the base case, so the first vertex is always marked. And yeah, and that's exactly what we wrote. Okay, so if I is Vi is marked, then Vi plus 1 is marked. Okay, so this is the summary of it. Alright, so what is the running time? Okay, so this is the algorithm, I just rewrote it. So what would be the running time of this? And how would you bound the running time of this?
If we are not storing the neighbors explicitly, then we need to search for the neighbors, and then it would take a lot of time.
What do you mean by a lot?
I mean, it will take a linear time.
Okay, so yeah. Yeah, so as I said, any running time analysis, all you have to do is go through the algorithm and see step by step how long each step takes, right? So the first step of this, which is you're running explore on this vertex U. And the first step of explore is you just set reachability, so that's just a constant thing because you're maintaining an array. And you go through the neighbors of this vertex, and if it's not reachable, you run explore. Right, so how long does this take? So what he was saying is that if you don't really have an adjacency list for the neighbors of W, then you actually take, when finding neighbors, takes time equal to size, number of vertices. Okay. So if you just had an adjacency matrix, and if you had a list, then this procedure takes time, which is essentially degree of W. So that's one point. So let's keep this in mind. Okay, so that's what it takes when you have to iterate through the neighbors. And each time what you do, you check if it was reachable, and otherwise you run explore on the other thing. Okay. So how would you formalize this, right? So earlier we just said, oh, write some inductive statement, I mean some inductive claim on that, right? So some inductive, if you remember last time we had a problem size which was the n, which is the length of the array that we were doing the recursive step on, and we wrote something like t of n is 1 plus t of n by 2. But in this case, there's no natural notion of a problem size, right? Because you're running explore on a different vertex of the same graph. Okay, so it doesn't quite make sense. So how else would you argue in this case? Yeah.
Can we simply say that since we need to visit all the vertices at edges, and complexity becomes v plus e, in this case that it will be equal to v squared and
Slowly again.
so we can see that we will need to basically visit all the vertices in the worst case
Okay.
at h. So then we can say that for the worst case, the complexity will be v plus e.
Right. So that's what we would like to say, right? So yeah. So what? So I guess what he's observing is that the procedure explore is only called for any vertex at most once. Because you will never call explore of some vertex twice. Because each time you call it, you check if reachable was marked true or not. Okay? So this is one simple observation that we make. Okay, that explore of u is called at most once. Once per vertex. Okay. So in the very worst case, you could call it precisely once for every vertex. And for one vertex, we said that for one vertex w, we said that it takes time, which is degree of w, plus 1, I guess, because there was this first step of setting reachable equilibrium. So if you go by this, so the time without the recursive call was this, and now we are saying explore is only called at most once per vertex. So now you can bound the running time. Therefore, you can say the total running time is less than sum over all vertices w of 1 plus degree of w. Okay. And what is this? So what do the ones add up to? So the ones add up to. And what is the sum of the degrees of the edge? And so it's, to be precise, it's twice the number of edges, but as we use orientation, it's so the sum of the degrees is twice the number of edges, because every edge will be counted precisely twice. So that's this is the sum of the degrees. Okay. So the total running time is this, which is v plus. But note that if you had used just the adjacency matrix, then what you would have gotten is not this quantity, but you would have had 1 plus size of v, which actually is something like v squared. Okay. Which could be significantly worse. So the number of edges is bounded by v squared, but it could be much smaller, right? Usually, the number of edges is yeah. So for this kind of a problem, using an adjacency list turns out to be significantly better than using an adjacency matrix. Okay. So here's, I just want to give one example on where the running time depends on the data structure you use. Alright, so I guess we are a bit over time. So let's stop here, and so next class we'll do divided.